This is the 5-4 to 5-5 review, number 7, and calculators are still not allowed. I'm not going to let you use the calculators on any of these substitution methods because you could just do them on your calculator, and I want you to know the process by hand. So, on number 7, we need to first ask ourselves, do I know what I took the derivative of with respect to x that gave me this nightmarish mess inside? And the answer, of course, is no. That is way more complicated than anything that's on my green sheet. So, my next line of defense is to try and figure out if I have a function that is inside another function that serves multiple purposes. The first is it inside something that's easy to go backwards on? The second thing is its derivative also in the integral? And the third thing is that derivative enough to cancel out all the leftovers? So if I look at this, the first thing that I notice that's kind of inside something else is this tangent of x. And it's inside a root, which is actually going to be a power rule. I know how to go backwards on power rules, so that's maybe a good option for me. And if I take the derivative of tangent, I get a secant squared. And secant is the reciprocal of cosine. So this 1 over cosine squared is the same as a secant squared. So the derivative is in there, and that's the only leftovers. So tangent is going to be a good choice for me, and I'm going to use it. So I will write down that u equals the tangent of x. Once I have my u, the next thing is to figure out what dx is. Well, dx is my du over the derivative of this, which is secant squared. The next thing I do is I go back to my integral and I rewrite everything, replacing the u's and the dx. So I'll have a u over a cosine squared times a du over a secant squared. Well, cosine and secant are inverses of each other, so those, when I multiply them together, are just going to give me 1. So I will be left with a u to the 1/2 times a du. Now we also, because we have a definite integral, need to think about what the limits are going to be in the u setting. So if I plug 0 into tangent, I get the tangent of 0, which is 0. And if I have pi over 4 as my upper limit, plug pi over 4 in here, I get the tangent of 1, which is 1. Or excuse me, tangent of pi over 4, which is 1. So my upper is 1. Now I'm ready to answer the question because I've created an easy integral. What do I take the derivative of with respect to u that gives me a u to the 1/2? I do the power rule backwards and evaluate from 0 to 1. So dividing by 3/2 is the same as multiplying by 2/3. If I plug in 1, I'm getting 1. If I plug in 0, I get a 0. So I end up with a 2/3 minus 0, or a 2/3. If I look on the next one, b. Same sort of issue here. I need to look for a u whose derivative is in there, and it also tends to be inside something else. So I can see right here that I've got a secant that is inside an exponential. So that's probably my best choice for my u. And if I take the derivative of secant, I get a secant tangent. Well, secant is the reciprocal of cosine, so I have a secant tangent inside the integral, and it's all the leftovers. So that indeed is a good choice for u, and I will write it down. U equals the secant of x. I can now find out that dx is du over the secant tangent. And then I can do my substitution. So things that are in the boxes get replaced, everything else stays the same. So I have an e to the u times a tangent over a cosine times a du over a secant times a tangent. Well, the tangents are going to cancel, and cosine and secant are multiplicative inverses, so when I multiply them, I'll get a 1. So I'm going to be left with just an e to the u times a du. Now if we go back, we notice that this was a definite integral, so I have to change my limits. If I plug 0 into the secant, that's 1 over the cosine of 0, which is 1 over 1, which gives me a lower limit of 1. If I plug pi over 3 in, that's going to be 1 over the cosine of pi over 3. Remember, cosine is the x coordinate on the unit circle. So at pi over 3, the x coordinate is 1/2. So the reciprocal of that is going to be 2. I'm ready to answer the question posed by the symbol. What did I take the derivative of with respect to u that gives me e to the u? And I get e to the u from 1 to 2. I plug the 2 in, and I plug the 1 in, and I'm done. Last one, C. We again look for a function that is inside another function, and we can see that cotangent is inside that exponential. The derivative of cotangent is a negative cosecant squared, which is the reciprocal of a sine squared. So that's in there, and it's all our leftovers. So that's a good choice for my u. U will be cotangent of x, dx will be du over a negative cosecant squared of x, which means when I do my replacement, I'll get e to the u over a sine squared times a du over a negative cosecant squared. Well, sine and cosecant are inverses. When I multiply them, I'm going to get a 1, and I can pull this negative out in front. Because I have a definite integral, I've got to track my limits with me. So the cotangent of pi over 4 is the same as the reciprocal of the tangent of pi over 4. And the tangent of pi over 4 is a 1. So that cotangent of pi over 4 will also be a 1. Cotangent of pi over 2 is going to be the cosine of pi over 2 over the sine of pi over 2. Well, the cosine of pi over 2 is 0. The sine of pi over 2 is 1. So we're going to have an upper limit of 0. So if I finish this, we can see that I've got the opposite of an integral that's going backwards. So we can either do the antiderivative and take its opposite, or we can switch the limits right now. So we're going in the right order and change that sign. So now we're ready to answer the question posed by that symbol. What did I take the derivative of with respect to u that gave me e to the u? Well, that's just e to the u from 0 to 1. If I plug in a 1, I get e. If I plug in a 0, I get 1. So my answer is e minus 1.